Alright guys, welcome to lecture 3 of this RISC-V processor design course. On the previous lecture we explored most of the combinatorial logic that we're gonna need for the rest of the course. We're gonna explore one more thing on the combinatorial logic side of things, and then we'll move to sequential logic, register transfer logic, register files, and memory, and we'll wrap up this lecture. The last thing we briefly touched upon on the last few minutes of the previous lectures were the case statements, and what we were really doing there was inferencing a multiplexer. We now formalize the concept of a multiplexer, and what a multiplexer is a combinatorial logic circuit that selects one of several input signals and routes it to a single output line based on the value of the select lines. So you can think of it as a semaphore that decides whether an input signal goes to the output based on another input signal, which we typically call as select line. So this is what a 2-to-1 multiplexer looks like. We need to select between two inputs, so one select bit is fine. And you can see that when S0 is 0, we hard connect input 0 to the output regardless of what input 1 is. So this is why you have hexes here. And then when S0 switches to 1, the same thing applies, but for input 1. So we're basically passing input 1 to the output. So we have a few ways of coding a multiplexer in System Verilog, and one is a ternary operator. If you did some C code, this is something that you definitely saw during the lectures. And here we have two 32-bit input signals. We have a select line, and then we have an output signal, which is the same width of the input signals. So here we assign output based on S0. So if S0 is a true condition, so if S0 is 1, we put I1 to out, otherwise we put I0. So this is pretty much what we saw in the truth table in the previous slides. This notion is extremely handy if you have a simple condition to evaluate. Otherwise, it becomes a spaghetti mess. If you have more than two inputs, it becomes extremely hard to debug, and a lot of bugs I have seen come from the improper use or nested use of the ternary operator. So again, we're gonna use it from time to time. We'll try to avoid it as much as possible. Another notation that I personally like a lot is this OR of AND, and these follows the min term approach if you did some digital design lectures, and it's the same thing, behaves in the same way that we had seen previously with the ternary operator. The nice thing that you can have here is that you can allow a non-full tree, meaning that you can have multiple conditions and you don't have to exhaust all possible conditions for select signals. This is not something that's going to be extremely clear now. We're going to see when we start building the processor what this really means. But as of now, it allows for more complex conditions to be evaluated. And the problem is that it may not be recognized as a multiplexer by some synthesis tools. If your intention is to build a straight up multiplexer, you need to go with the next approach, which is the one that we saw, and it's the case statement. And the case statement enumerates all the cases that are possible as 0. You can have missing cases. You can get away with not having a default statement. It's going to cause problems when you implement this multiplexer, but this allows for the most complex conditions to be evaluated, and synthesis tools will always recognize this thing as a multiplexer. Are they gonna optimize it the way you want it? This is something that you need to clarify for the synthesis tool to do. So you have different kind of case statements. You have case Z, and case X. So case is the most basic form of a multiplexer. Case, which if I'm not mistaken is the one that we used in the previous lecture, is a variant that allows for don't care condition. So if you want to implement priority encoders, but you need to know what you're doing there. You can do so by case GAC. One that you should never use is the case X, which is a variant that allows for don't care conditions and don't care values. So X propagates. Whenever you have a case X, X in the inputs can propagate to the output, and this causes a lot of issues, especially when using Verilator where you don't have X's, so it becomes even more challenging to debug. One thing that we can do to make sure that the synthesis tool does the best job at optimizing these multiplexers, because they tend to become extremely large, is to put a qualifier for a case statement that allows for unique selection of the case, meaning that if you know upfront that only one of the different case conditions is going to be true at a given time when evaluating the case statement, you should use unique, because this tells to the synthesis tool that only one case will be true at any given time, so it can evaluate all the cases in parallel instead of serializing those. And what happens if two conditions are true? The simulator will either throw an error or a warning. It really depends on the simulator. I think you can bump it up. If it's a warning, you can bump it up to an error, but it really depends on the simulator you're using. We now start our journey into the sequential logic. From the previous lecture, we classified logic mostly two categories: combinatorial, the outputs depend solely on the inputs at a given time that we are evaluating the circuit. Sequential logic is a type of logic that depends on the past and present values of the inputs to determine the present output. It is characterized by the presence of latches and flip-flops. We're going to quickly get out of the way the latches and difference between latches and flip-flops. So latches are still combinatorial logic circuits that store the value of their input signal, while flip-flops are sequential logic circuits that store the value of the input signal. So that there's a slight difference between the two, and a latch, as you can see, is a fairly straightforward piece of logic. For here you have a set and reset latch, and a set and reset latch is again a combinatorial logic circuit that stores the input value, and we can basically perform two actions on this latch, so either set it or reset it. When we set it, the output becomes 1, so Q is the output, and then you have Q negated, and when you reset it, it goes to 0. The reset adds priority over the set input, and if both inputs are 0, the Q value is whatever was before. So this is why it stores the value, and the storing ability of this circuit derives from these feedback loops, so this one and this other one. And the problem with latches is that they can cause hazards. So a hazard is a situation where the output of a circuit is not determined by the current input. You can think of it, you sampled an X down the line. You should never intentionally put latches in your design. So latches are a bad practice and should be avoided. We're going to see how, when, and where we're going to mistakenly put latches inside our design. So when we mistakenly put a latch inside our design, we call it latch inferring. So we wrote a piece of code that somehow the synthesizer or the simulator determined to be a latch. And this happens if they either detect a combo loop, or if you forgot a signal from the sensitivity list in an always block. And this is why we use always comb and always FF statements to avoid to have to put a sensitivity list by hand every time. And this happened in Verilog because we didn't have those constructs in system. Verilog is taken care of. Or if you're using a blocking assignment in a procedural block, and this may seem very cryptic right now. We're going to see what this means in a few more slides. So combo. So this doesn't cause any issue because here the statements are assigned in a sequential manner inside the always statement. It can be comb, flip-flop, or always, simple always statement with a sensitivity list. So that the fact that we are assigning 2 times out is not an issue because only the last one will prevail. But the problem with the last one is that it feeds back the out of this one. So this is a very nasty example, but just to say that you're not supposed to feed back a signal inside an equation and then sampling it back, because otherwise, what's the value here? What's gonna be the value here? So you can have like oscillating signal. We're not doing SRAM. If you forget a signal in the sensitivity list, as we said, it's going to infer a latch anyways, because for example here you're saying that this always statement is sensitive only to A and B, but it truly depends on C as well. So what happens to out when C changes? Well, the way it's written right now, out shouldn't change when C changes. So where does that out value gets stored when the C variable changes? It will be stored in a latch. And so this is not going to behave the way you want it, because this is a 3-input AND function. Well, what you got is a 2-input AND ended with the old value of C. Now that we cleared the air about latches, we can start dealing with true sequential logic. And we cannot start dealing with sequential logic unless we introduce two very important signals, which is the clock and the reset. So clock and reset are two signals that are used to synchronize the circuit. So whenever you have sequential logic, you have to synchronize the whole system, and clock is used to synchronize the circuit itself, and reset is used to bring the circuit to a known state. A few words on the clock signal. As we said, it's a signal that's used to synchronize all the memory elements of the circuit, and it's basically a square wave signal that oscillates between logic 0 and logic 1. And it has a few parameters that are interesting. Has a period and a duty cycle. So the period is how much time it takes for it to complete a 1-0 or 0-1 cycle. And the duty cycle is the percentage of how much time we have a one value and compare it to the whole time. A 50% duty cycle means that the clock signal 50% of the time at 1, 50% of the time at 0. And the inverse of the period is the frequency measured in hertz. So this is what your processor, when you buy it off the shelf, it says it's a 3 gigahertz processor. It means the clock cycle of that processor is 3 gigahertz. It's not that simple, because you have technologies like turbo boost. You can dynamically lower the frequency. Let's say the clock cycle is proportional to how many things can happen inside the design in a given amount of time. What makes the clock signal the fastest signal you can have in your design? All the other signals are clocked, meaning they change at the rising edge or the falling edge of the clock signal. And we're going to see what this means. So this means that the fastest known clock signal has half the frequency of the clock signal. Because if we consider only the rising edges or the falling edges, you have half as much as the combination of the two of them. So distributing the clock signal through the design is the most challenging part for the purpose of this course. We don't care about who generates this clock signal, who distributes it, or how it's distributed. So we only care about the fact that this clock signal is being distributed by somebody. We have access to it, and we are going to cover all the best coding practices in this series of lectures on how to deal with the clock cycle. And let me say a few things here regarding the difference between FPGAs and custom chips, so ASICs. The way you deal with clock in FPGAs and ASICs, it is completely different. For one, in the FPGA, the clock network is already provided to you, and it has very special networks to distribute these clock cycles. While in the ASIC, you have a white canvas. You can pretty much do whatever you want with the clock up to a certain point. The reset signal is a signal that is used to bring the circuit to a known state, all zeros, all ones, initialize memories, whatever. And it is typically provided externally, and later synchronized to the clock signal. So you can think of it as a button that somebody presses. So if it's a hardware reset, that reset signal is then sampled with the clock cycle and then distributed inside the chip. We can now start look at the first sequential element, which is the D flip-flop, and the D stands for data. Without reset, the simplest form of a D flip-flop. And it is characterized by the presence of a clock signal. This is the transition diagram that we see. So you can see the clock goes up and down, up and down, up and down. And you can see that D can change at any time. Okay, it doesn't have to be synchronized with the clock. So D can change at any time. The arrow on the clock signal represents when we sample the D signal. So what happens is here we sample D is 1, Q is 1. Then nothing happens until the next rising edge. And until the next rising edge, we go look at the D. D is 0, and so Q goes down. And on the next clock cycle, D is 0 and Q goes down. So we missed some information in terms of what happened to D and what happened to Q, but this is not the point. The point is that Q follows D on the rising edge of the clock cycle. So this is how the D flip-flop works. And you can see it here in the code base associated with this lecture that you can download at the link below. If you go on the terminal and you go into the repo under docs lecture 3 code, you will find a RTL and DV folder with a make file. You can type make all and it's going to make the test benches. And if we open up flops.vcd with GTK, so with this command GTK wave flops.vcd, this one is going to pop up. And under top flopsdb, we have the 3 different flops that we're going to see throughout this lecture. The first one is the one that I was showing you. And if we pull up the signals, you can see that we have a clock that goes up and down, up and down, up and down. If you open up the test bench, you're going to find out that this is a 100 megahertz clock. Doesn't matter. It could have been like 1 terahertz. For simulation purposes, it was going to be this. Here, we're looking at the rising edge of the clock to sample. So what happens here, rising edge comes up, D is 1, we transfer 1 to the output. Here it falls, but we're not sampling on the falling. Going back to our slides, this is the architecture of the D flip-flop, and as you can see, we have a negative level sensitive latch in series to a positive level sensitive latch, and the first one you can see is negative sensitive because the clock cycle is there's a NOT gate, and then we NOT again here, so here is the clock cycle. And so this gives us a narrow window where we are sampling the signal between the negative level and the positive level of the clock cycle. So notice level and edge here. It is not important for our purposes to know how the D flip-flop architecture is made. There are many different architectures, many different optimizations. If you're implementing on FPGA, the flops are going to be there for you. And if you're doing ASICs, the process development kit, which is basically the set of primitives that the fab already has made for you available to use, the D flip-flop is going to be there as well. How do we code a D flip-flop? So we have 2 inputs, 1 output. So the clock and the D input, the data input, and a Q output, which is a 1 clock cycle delay of the D input sampled at the positive edge. So if here we change the keyword and we put neg edge, we would be sampling at the negative edge of the clock. So here there's a few things to note. So one is the use of the always FF construct, the positive edge of the clock inside the sensitivity list of the always FF construct. And then here the use of this non-blocking procedural statement for assigning D to Q. So this means that we can evaluate whatever it's in here in parallel and not sequentially, meaning that if we had another assignment down here, it will be evaluated in parallel to this first assignment. So the general rule is to use this symbol, so the non-blocking assignment, whenever we are in a clock domain. Here is explained blocking versus non-blocking assignments. Blocking assignments are used for combinatorial logic and non-blocking assignments are used for sequential logic. So this is wrong. Using a blocking assignment inside a piece of sequential logic is wrong. It's likely gonna throw an error on the simulator, and if not, it's gonna throw an error on the synthesizer. So throughout the course, we're gonna avoid as much as possible to put these always FF statements, because they are a source of bugs, especially when you have tons of flops in your design. So we're gonna build a library of flops that we can then instantiate in our design, knowing that the always FF statement that it's in there is already been tested. So this is how we can build a reusable and scalable set of primitives that we can then reuse throughout our design. Then we have a D flip-flop with synchronous reset. It has a reset signal. So here, of course, the module is cut out, but whatever we need, it's displayed correctly. You can see the full code inside the code base. And we added a reset N to the input port. And what this reset N means is that when the reset is 0, we assign 0 to Q, so the output. Otherwise, we sample D at the rising edge of the clock cycle and transfer it to Q. So this portion is the same thing as the previous one, but now we have this reset condition which brings the flop at a known state. Because in the previous case here, we didn't know originally what is in Q. So suppose I have this flop, I power it. What is the output of Q? Is it 0? Is it 1? I don't know. So that's why we have synchronous reset flops. What does it mean that this is a synchronous reset flop? It means that the reset is not part of the sensitive release of the always FF statement. Sometimes you can see that you have the reset that appears here, either at the negative edge or at the positive edge. That is a synchronous reset, and we're going to see what that means, when to use it, when not to use it, that there's a few caveats there. But if we look at the waveforms for that flop here, you can see that basically the reset brings Q to a known state, which is 0. And then when reset comes high, which comes high throughout the rest of our simulation, the flop behaves exactly as it did before. Since we're using a two-state simulator, we are not going to experience the difference between this one and the previous one. But if we were to use a four-state simulator, you would see that the Q output of the previous flop without the reset would have been an X. Back to the slides. We briefly talked about the asynchronous reset, and this is where things start to become a little bit more interesting, meaning that now you have also the reset into the sensitivity list of the flop. And what this means is that the difference between the synchronous reset and the asynchronous reset is that when we issue a reset here, the reset does not happen until the next rising edge of the clock cycle. While here, the asynchronous reset happens as fast as the falling edge of the... And when do we use one? When do we use another? It really depends on the platform where your circuit will be implemented. So for FPGAs, consult the documentation of the FPGA vendor. He's going to tell you which kind of flops you want to use, and if there are different kind of flops available for you to use. And for ASICs, You have to consult the process design kit documentation, so the PDK of the foundry that you're using. We will use synchronous reset in this course since we assume that the reset has been properly synchronized outside with the clock signal prior to entering the design. So this is what we're going to use. So we're going to use the first variant of the reset D flip-flop. You can have more variants. This is the last one that we're going to see. There are many different flops, but basically with this set of flops that we saw, you can do pretty much anything. So this is a D flip-flop with a synchronous reset. I didn't put it here because we assume throughout the course that we're going to use a synchronous reset flop and an enable. After we brought the flop to a known state, which can be 0, which can be 1, you can configure it, you can do pretty much what you want. The enable signal acts as a gate between D and Q. And here on the slides, it solves merge dot. So we're gonna open it here on the editor. And this is what it looks like. We have the clock, the reset, the D, the enable, and the Q. So if you think about it, it decides after the reset has been deasserted, how and when the Q follows the D input. Okay, and if we look at the waveforms, here we have, you can see here reset is deasserted. So now we are working properly. So here you can see D and enable go to 1 and Q goes to 1. But here, when we sample D becomes 0, but since the enable is 0, we don't change the output. Okay, so enable acts as basically a gate between D and Q and decides if D transfers to Q or not. Now that we saw the D flip-flop with all its variants of reset, enable, and whatnot, we can combine D flip-flops to create larger structures like a register. And what a register is, it's nothing else than a bank of flops put in parallel, and that's pretty much it. So they all share the same clock, and in this case we have a 32-bit register, and we assign the 32-bit input to the 32-bit output on the rising edge of the clock. Pretty much the same thing as a D flip-flop, but now instead of being a single bit, we have 32 bits. And whatever we saw with the D flip-flop can be extended to the register. So we have registers with reset and registers with reset and enable. We can see them briefly on the code base. And you can see, let's take only the D flip-flop and let's see what we mean by that. So D here on this negative edge of the clock cycle assumes this value, and you can see it gets transferred to the output Q at this other clock cycle. And the same thing for the other ones. So we basically extended the logic of a D flip-flop to the whole bank of flops, which we call a register. Now, where it gets interesting is now we combined the flops. If you want to visualize it, we combine the flops horizontally. What happens if we stack the flops vertically? So we know that if we stack them horizontally, we get a register. If we stack them also vertically, we obtain a register file. So what is a register file? It's a collection of registers. So a collection of flops is a register. A collection of registers is a register file. And what a register file is a structure that gets clock and reset is a sequential element, so it goes without saying. It gets a data input. It gets a read address, a write address, a write enable, and a data out. So you can visualize this thing as something that contains multiple registers, and we decide which register to read and which register to write with the read address for the read and write address and write enabled for the write. So here in this case we have 4. So here we have n, which is 4 32-bit registers. So what happens here is that if we reset all the registers, and otherwise we write the registers whenever we have a write enabled. The registers are captured into this variable which has 2 dimensions. The first dimension is the width of the single register, so how many bits is a single register, and the second dimension, which is the vertical one, is how many of them we have. So if we want to extend this register file to RISC-V to support the RV32 instruction set architecture, n would be 32 and the width would be 32. And in particular, the size of the read address and write address is going to be the base 2 logarithm of whatever n. So for example, here n equals 4, we just need 2 bit for the read address and the write address, because we can have as many as 4 combinations for the various addresses. So this is the relationship between how many registers we have and the read address, and data in and data out have to be the same width of the individual register. So you can see here that the write to the register file is synchronous, meaning that we can only write at the positive edge of the clock, because if you remember, the positive edge is where the flops get updated. So you can think this as the queue of the flop, but the data out can be read anytime we want, because it typically happens with some decoders which are combinatorial logic by design. Okay, so this is the difference here between the read path and the write path. Let's look at the test bench for a minute. So this is the test bench for the register file. And what we do is we reset the register file first here, then we assert normal operation and we write to the 0 address whatever number we want. So this is a system call that gives us a random number. After 1 clock cycle, we deassert the write enable, and then we issue another transaction, another write transaction, this time to the first register. So address number 1, we write 1 and we deassert the write enable, and then we issue 2 read transactions, one for the read address and another one for the one read address. And you can see here I've added a read enable to this register file. Sometimes you have it, sometimes you don't. This is really depends on how critical the power is in your system. We're gonna assume that for our tiny Vedas processor, we're gonna have a read enable. Sometimes you, as I said, sometimes you have it, sometimes you don't. So if we run this test bench, what we expect is to read here in these 2 read transaction what we wrote here. And we're gonna see this on the terminal because it's a lot easier than to look at the waveforms. Let's do a make register file sim from our code base. Let's hit enter. And you can see that here we are writing to address 0, so write enable is 1. This data, whatever it is, this is the random data that we generated, and we are reading back that data when we read from address 0 with read enable 1, and the same thing goes for address 1. When we write, we read back the same value. So this is how the register file works. Now we can have crazy architectures for register files, and this typically happens in very high performance cores that a lot of operations are happening in parallel, and you need more than one port to the register file, more than one read port, more than one write port. It doesn't have to be symmetrical. It can be basically whatever you want. We're gonna see that on our RISC-V 32-bit processor, we're gonna need one write port and two read ports, because RISC-V instructions, at least the ones that we're gonna deal with, are gonna have two source operands and one destination operand. So this is what the structure will look like for a two read port, one write port register file. It's basically the same thing, but now we have more read ports and write ports, and we need to take into account that with these four statements. And you have a test bench for this register file. It doesn't make sense to go into that. It's pretty much the same structure that we saw, just that we have more ports that happen in. We are at the last piece of sequential logic that we're gonna see today, and it's memory. And this is a huge topic when it comes to chip design. We have many different types of memories. Here we will focus only on static RAM memories without even entering into the detail of how that memory is implemented. But the reason why we'll focus on this is they are the most typical memory that you can find in both FPGAs. So Xilinx calls them block RAMs or ultra RAMs, or in modern PDKs. And typically modern PDKs have some sort of Python scripts that you can generate memories, and they call it a memory compiler. So what's the difference between memory and the register file? Well, the underlying difference is the architecture that is used to store data. So in the memory, we're going to deal with an SRAM 6 transistor cell. Again, this is not the time or the place to enter into the details. While a register file has a flip-flop structure, which is a much larger, it involves much more transistors. And a register file has a combinatorial read port and a sequential write port, while memory has both read and write ports sequential. And memory is much harder to reset in the conventional way that we saw to reset a register file just with a bit switch on the reset line. So if we look at the test bench, the fact that the read port is sequential in this case is exemplified by the fact that the read operation, to make sure we correctly read from the read port, we need to wait an additional clock cycle. This is why here you have two positive edge clock waiting. And this is best saw in the terminal here, where if we make the memory simulation, you can see that it's pretty much the same thing as the register file, where we read from address 0, where we wrote this value, and the same thing for address 1, and we get the same data. So we successfully store data. So it's same structure externally from a black box perspective, but we have a sequential read port instead of having a combinatorial read port. So before wrapping this lecture up, I want to discuss why we saw all of this. We saw all of this because throughout the next lectures, we're going to write code in a way that is called register transfer level. This way of coding hardware works is that we see everything as a bank of registers separated by combinatorial logic. So the way this is going to work is we're going to set up stages of flops divided by combinatorial logic. We're going to define an instruction fetch stage, an instruction decode stage, multiple execution stages, and what happens between those flop stages is going to determine how our processor works. So it's a very neat and packed way of describing RTL, where the combinatorial logic is used to transfer and transform the data between registers, flops, register file, whatever you want to have. And sequential logic is used to store the data. Thanks for staying on, and we're going to start next lecture diving deep into RISC-V, what it is, and how to get started coding some stuff.